Anions form when an atom gains electrons, and cations form when an atom loses electrons. And those electrons are generally lost from the valence shell. So we don't really have many issues with making the anions. We just add another electron into the next available orbital. But when we make cations, we have to be a little bit careful. For the main group elements, the metals in the main group, for the cation, you just remove in reverse order of filling. So if you look at the aluminum, it filled in the order 1s, 2s, 2p, 3s, 3p. And so we're going to peel electrons off in reverse order. We're going to take off the 3p, and then we're going to take off the 2 3s electrons. And this will be the electron configuration for an aluminum ion. Okay? The transition metals are a little squirrely. They're not as predictable. What we do here is we remove the valence electrons first, even if that is not the same as the reverse order of filling. So here's the electron configuration for iron. We identify the valence electrons by looking for the highest principal quantum number. That's right there, 4s. Iron has 2 valence electrons. Those 3d electrons are not considered valence electrons. So we're going to remove the valence electrons first, and that would give us an Fe2 plus cation with this electron configuration. If we're going to make an Fe3 plus, we've already removed the valence electrons. Now we will go with reverse order of filling, and we'll take off one of these 3d electrons, and this would be the electron configuration for iron 3 plus. Any questions? Electron configurations, especially the orbital diagrams, can help us predict whether something will be magnetic or not. Some metals are attracted to magnets and some are not. And it has to do with the electrons, whether they're paired or unpaired in the individual atoms. So we say an atom is paramagnetic if it has unpaired electrons. I always have a hard time remembering that because I think, you hear the prefix para and you think pair, right? So that's the paired. No, it's backwards. The paramagnetic has unpaired electrons. Things with unpaired electrons will be attracted to a magnetic field. Those unpaired electrons actually generate their own little magnetic field because of the spinning of that charge. Diamagnetic atoms or ions have all of their electrons paired up, and so they are actually slightly repelled by a magnetic field. They're definitely not attracted. So paramagnetic means there are unpaired electrons. So let's look at 2 examples of this. Write the electron configuration and orbital diagram for each ion. Predict whether each will be paramagnetic or diamagnetic. And we're just going to look at the noble gas configuration because all those core electrons really don't matter at all in this. So for cobalt, the previous noble gas is argon. So we've got argon. And then we go along on the periodic table after argon, and what's next? We're now in the 4th period, and the first 2 columns are the S blocks. We've got 4s2, and then next we get into that D block. That's 3d, and how many electrons do we put in there? 1, 2, 3, 4, 5, 6, 7? 7. That's the cobalt atom. That's where you need to start for transition elements. And then let's draw just this part for the orbital diagram. And so that would have 2 electrons in here, 1, 2, 3, 4, 5, 6, 7 electrons in there. So this is a cobalt 2 plus. We need to remove 2 of those electrons. Which ones do we take out? 3. The 3d?
No, the
the 4s. I forgot to label this one. We want to remove the valence electrons. So we're going to get rid of those. We're taking out 2. And so now we have a cobalt-2 ion. So we need to change this. That would be 0, but we normally just wouldn't write that at all. So I'll just kind of put that in parentheses. Does the cobalt-2 plus ion have unpaired electrons? Yes, it does. It has 3 of them in this 3D sublevel. So is it paramagnetic or diamagnetic? Para. Para because it has unpaired.
Is that because, like, those particular rooms, in other words, or the shells, are like exposed to the proton force of that particular atom, therefore making it more magnetic?
Well, what happens is when you have these electrons spinning by themselves, they create a small magnetic field. When you have the paired electrons, you could think of their magnetic fields as kind of canceling each other out. So if they're all paired up, then there's no magnetic field. When they're unpaired, the atom has its own little magnetic field, and that magnetic field interacts with an outside magnetic field. Any other questions? So we would expect cobalt-2 plus ions to be attracted to magnetic fields, to interact. Let's look at the nitrogen ion. So it would be helium. We'll do nitrogen first. 2s2 and then 2p2, right? No, 3. So that's nitrogen. The 3 minus charge says we've added 3 electrons, right? So this 3 becomes a 6. So there's the electron configuration for nitrogen. Let's draw the orbital diagram. There's 2s, and here's 2p. We've got 2 electrons in there, and 1, 2, 3, 4, 5, 6 electrons in there. Are there any unpaired electrons? No. They're all paired. So the nitrogen ion, dinitrogen, what? Is diamagnetic.
So diamagnetic means
It won't, no. It'll be slightly repelled, but it really is not that noticeable. So, I find that, like I said, the para and the diamagnetic confusing. So in my mind, di means 2, and they're all in 2s. So in the diamagnetic, all the electrons come 2 by 2, like Noah's Ark. The paramagnetic, then we have unpaired electrons. Any questions? Yeah.
Does this have anything to do with like polarity in atoms and stuff?
This doesn't really have much to do with polarity in atoms, no. But it does have to do in molecules, yeah. It doesn't have to do with polarity in molecules. That has more to do with electronegativity. We looked at size of atoms. Let's look at sizes of ions. So comparing a neutral atom with a cation. Cations are much smaller. And this makes sense intuitively. I always love it when things just kind of make sense. How do you make a cation? You take electrons off, right? You're taking the valence electrons off, usually all of them. So it's like peeling the outer layer of the onion off. The onion's smaller now, right? So we peel off some electrons and it gets smaller. Now the change is larger than we might expect because we now have a higher effective nuclear charge. Because under that first layer on the outside is a second layer, and now that second layer is the outside layer. And so there you've lost some of your shielding of the core electrons, and so you have a higher effective nuclear charge. So we see these very dramatic differences. So on the left here is the atom, and on the right is the cation. Changes a lot. Anions are the opposite. They get bigger. So we're adding electrons. They're not going into a higher principal energy level, but they're adding electrons, and we're experiencing a lower effective nuclear charge. And so the atoms get larger as ions. The word isoelectronic, iso is a prefix that means the same. So this means same electrons. You can have several ions that have the same number of electrons. They're not the same element because the number of protons is different. So here's an example. Sulfide ion, chloride ion, potassium ion, and calcium ion. They all have 18 electrons, but they have different numbers of protons. So those 18 electrons are going to be arranged in the same way. They're all going to be the same as argon, and so it's going to end in, their electron configurations are going to end in 3s2, 3p6. They're all the same. So you might say, well, then maybe the sizes are the same. But now we have to consider effective nuclear charge. Sulfur has 16 protons, chlorine has 17, potassium has 19, and calcium has 20. So higher effective nuclear charge means smaller ion. So calcium is the smallest, and sulfide is the largest. And those are the actual measurements. Choose the larger atom or ion from each pair. So potassium atom or potassium ion? The larger. Potassium ion not, yes. Potassium atom. And I really think the best way to remember this is to be able to think about it. So how do I go from a potassium atom to a K+ ion? I remove the valence electron. I'm peeling off the outer layer. It's getting smaller. So the potassium atom is larger. Comparing fluorine and fluoride. Which one's bigger? Fluoride. Because to take the fluorine atom and make it into a fluorine ion, I have to add an electron onto the outside. And regardless of the amount of how much it changes, putting something extra on the outside should make it bigger. So the fluoride ion is larger. Now these two, one's a cation, one's an anion. They're two different elements. We're only going to do isoelectronic ones. And it may not be obvious, but these are isoelectronic. Right? So calcium has 20 protons. 20 protons, 18 electrons. Chlorine has 17 protons and 18 electrons. The effective nuclear charge is greater on the calcium. There's a higher attraction for the electrons. They pull in, and so the chloride is larger. Any questions? Ionization energy. How do you make those ions? Well, to make a positive ion, a cation, you have to remove an electron. That always requires energy. I tend to talk about like the alkali metals. Well, sodium wants to be a sodium ion. It wants to lose an electron so it can look like neon. Yeah. But there is a cost involved. You do have to put energy in to pull the electron off. So the ionization energy is always positive. So to take one electron off, you put this ionization energy into it, and you pull off an electron, you get a +1 ion. You can also go in there and take off a second one, and you'll get a +2 ion. And you're removing one electron at a time. So IE2 is the second ionization energy. That's removing an electron from a +1 ion. And that's generally going to be larger than the first ionization energy. So what we observe is that as we go down a group from helium, neon, argon, krypton, xenon, the first ionization energy decreases. It becomes easier as the atom gets larger to take an electron on. I hesitate to say this knowing it's going to be on YouTube for the world, but so think about a mom who has 2 kids and a mom who has 6 kids, and they're both going to the big Fresno fair. Who would it be easier to kidnap a child from? The mom with 2 kids or the mom with 6? 6, right? You cannot hold on to 6 children at once, and you really cannot depend on them to hold on to each other. The children are going to be farther away, and she can't pay attention to them. It's easier to take an electron from a larger atom. The distance between that electron and the nucleus is larger, and so it's not held as tightly. So as we go down, it makes sense that gets larger. The trend going across a period is kind of jagged. So there's some little exceptions in here, but generally it increases as we go across. That's following the same trend. As you go across a period, the atoms get smaller. It's harder to take an electron off of a smaller atom. It's easier to take it off of a bigger. So we see that the ionization energy increases as we go across. So ionization energy and atomic size are trends that are exactly opposite to each other. Here's the other type of a graph showing this. So we see ionization energy decreases as we're coming down, and it increases as we go across. So on the basis of trends, determine which of these in each pair has a higher first ionization energy. Tin or iodine? So on the periodic table, we've got tin over here, and then we've got some things, and we've got iodine. Oops. They're in the same period. Tin will have the higher first ionization energy. Let's think about size. Which one's bigger, tin or iodine? Tin is bigger. Is it easier to take a child from a large family or a small family? Large. So it's easier to take it from tin. So that means the ionization energy is lower. Yeah. So iodine has the higher first ionization energy. It's so easy to get this backwards. You know, when I'm answering these questions, right now I'm saying it out loud, but this is what I do every time I would have to answer a question like this. I reason it out in my head because that's the only way I've found that I can do it. So let's look at calcium and strontium. So calcium is above strontium in the periodic table, directly above. So here's calcium and here's strontium. We're looking for higher first ionization energy. So we're looking for the smaller atom. Which one's smaller? Calcium. Carbon or phosphorus? Here's carbon, here's phosphorus. They're diagonal. Well, higher first ionization energy, we're looking for which of these is smaller. Going down, we'd say that the phosphorus would be smaller. Going across, we'd say that the carbon would be smaller going down. Going across, we'd say the phosphorus is smaller. So you could say it's not possible. I think that's a reasonable answer. What if we're forced to choose? Carbon. So I would say carbon for 2 reasons. One, the vertical trend is stronger than the horizontal trend. And also, are you familiar with any negative ions of phosphorus? Does phosphorus make anions? Yeah, it does. It's a P3 minus, but it doesn't make ions. Have we ever come across negative ions of carbon? No. So maybe carbon doesn't like to do that. So if you have to choose, I'd say carbon has a higher ionization energy. Fluorine or sulfur? Yeah, hands down fluorine. Because here the trends are coinciding with each other. Looking as we go down, fluorine, sulfur. Smaller. Fluorine is smaller. Going across, fluorine is smaller. So, yeah, wow. I need more cheesecake. That's what that means. Oh, exceptions, right? Got to be exceptions. So, I did point these out in that graph, this one. It goes up and comes down. It goes up and comes down. What's up with that? We see this exception between group 2A and group 3A. That boron has a smaller first ionization energy than beryllium, and that's not what we would expect based on periodic trends. What's happening is that boron is losing a 2p electron, whereas beryllium is losing a 2s electron. The 2p electrons have higher energy than the 2s electrons, and so they're a little easier to lose. Let's look at the orbital diagrams. So for boron, we've got 2 electrons in the 2s, and then we've got 1 in the 2p. Doing that from memory. Okay, yeah, I got that right. And then beryllium, we got the 2s, and the 2p is empty. Electrons fill in these orbitals in the order of 2s filling first and then 2p. They do that because the 2p orbital sublevel is a little higher in energy than the s. And so when we're removing this electron, because it's in a higher energy orbital, it's a little easier to remove than the s. And these guys are very similar in size and other things, and so the reason we see the exception is because we're removing electrons from different orbitals. That make sense? We see another exception between group 5A and 6A. And here we've got these things drawn out for us. So here's nitrogen in group 5A, and here's oxygen in group 6A. So for nitrogen, we've got a half-filled P sublevel. For oxygen, we do not. When we remove this 1 electron, then the oxygen has the half full. But this electron that we're going to remove is having to pair up. And so that makes it a little easier to remove than taking one of these. These guys have their own beds. They're pretty happy there. Here we've got this one guy who's like, yeah, I'm not so keen on sharing here. And so this is not quite as stable as these guys are. And so it's easier to remove this electron from oxygen, even though the trend, general trend, predicts otherwise. In successive ionization energies, the first to the second to the third, we also see the effect of what orbital is the electron in. If we look at sodium, when we remove that first electron, then sodium becomes isoelectronic with neon. It has the same electron configuration as neon. And so the first ionization energy for sodium is pretty small. That second one is a huge jump, almost 10 times as high as the first one. Because now you've gone into the previous core electrons and you've got a full shell, and it's much harder to remove those. And then this third one is also pretty high. For magnesium, removing the first one is a little harder than for sodium. Removing the second one is harder than the first, because now it's a positive charge and you're trying to remove an electron from it. It's going to be harder. But when we get the 2 electrons off, then magnesium is also isoelectronic with neon. And we've gotten down to a full shell. Taking that third one off, again, is a very huge leap in ionization energy. And that just does not happen much. Just doesn't happen. So you see this huge jump when that first core electron is being removed.